So this topic kind of makes me giggle sometimes when I think about, yes, we are always in motion. So for instance, if you tell a toddler, can you not sit still? The toddler will say, no, I cannot, and could go through these reasons of why he's always in motion. But we'll talk more about this, but there are different ways that we are always in motion. So for instance, the Earth spins on its axis of rotation. Okay, so you kind of get a sense for that rotation in this figure. Actually, if you are at the equator, okay, you are rotating 1,670 kilometers per hour, and if you're at the poles, not so much. Okay, that makes sense. All right, but another way we're always moving. So I guess somebody could say if you're at the poles, you're not moving, right? But one way that all latitudes on Earth are moving is that the Earth is orbiting the Sun. And I like this figure because there's all sorts of interesting things about this figure. Remember we said that one astronomical unit is the average distance between the Sun and the Earth. Notice that the Earth orbits the Sun in what we call kind of its own little frisbee, called the plane of the ecliptic, or the ecliptic plane. That's a good vocabulary word. Another thing, we'll be talking about more about this, is that the Earth's axis of rotation, okay, is always pointed, its north axis of rotation is always pointed to the star Polaris. That's our North Star right now. Okay, so its axis of rotation is tilted 23.5 degrees. You might be saying, well, 23.5 degrees, what's that an angle from? And to me, the best way I think is if you take a line and make it perpendicular with the ecliptic, okay, see how that's kind of perpendicular there, then the Earth is tilted from being, the Earth's axis of rotation is tilted from being perpendicular 23.5 degrees. Okay, so those are some important things. I guess another important thing is the direction of the Earth orbiting. So the Earth orbits counterclockwise. Can you see where this is going counterclockwise? The more we all have analog watches and clocks, that's going to be hard to kind of know what counterclockwise means. But the other thing is that the Earth is rotating on its axis counterclockwise. So it's orbiting counterclockwise and it's rotating counterclockwise on its axis of rotation as you look down at the North Pole. And that's not an accident. Actually, both of those kind of synchronous sort of rotation or spin and orbit in the same direction kind of came about quite naturally as the Earth was forming. Okay, so anyway, the point here is that's another sort of motion. And it says that actually the average speed is quite fast. Okay, the average speed is 107,000, kilometers per hour. Dang. So the next way that we're always moving is basically with our star. So here you see the Sun in a group of stars, okay, and you can kind of see the little green arrow show those stars kind of bobbing up and down a little bit, okay. They move a little bit random to each other, okay. But not random at all is this motion that you see here. Okay, so the Sun, the Sun, I might have said the Earth a minute ago. The Sun actually is orbiting the plane of our galaxy. So this is the Milky Way galaxy. Okay, and the Sun is taking a trip this way. Okay, I know it's showing clockwise, but that works, okay. So it takes, how long does it take for the Sun to complete one orbit? 230 million years. Okay, so is that not cool or what? And so there's that motion as well. Actually, it's this motion of the Sun as it orbits the center of our galaxy that you can take motion, observed motion like that, and understand something about the mass. So that kind of leads me to my next slide, where based upon the motion of the stars in the Milky Way galaxy, we know that the stars actually give us our light. Okay, so we see lit up, lit up, lit up. Okay, this is looking at the Milky Way galaxy. It's an artist's opinion or rendition of what the Milky Way galaxy would look like. This is the center of our galaxy. Actually, there is a black hole in the center of our galaxy. We'll talk more about that. It's a supermassive black hole there. But, so it's all lit up. But based upon the movement of the stars as they orbit the center of the galaxy, we know that there is a lot of mass in what we call the halo region. So this is called halo region. Anything that's not in the disk is in the halo. So we have a lot of, let's see, dark mass. How's that? You know where I'm going with this? Okay, so honestly, based upon the motion of the stars as they orbit the center of our galaxy, we know that we have a lot of dark matter here. And the Milky Way galaxy is not alone. We know that basically it's looking like all galaxies have dark matter in their halo region. And so when we look, and we'll talk more about this, when we look at how galaxies form, you know, the stars kind of hang together as a unit called a galaxy, actually dark matter, as it turns out, are an important player. What else are we moving? Oh, here we go. The raisin cake. I've personally never eaten raisin cake, but the raisin cake is supposed to kind of show our expanding universe. Remember I told you some 14 or some 13.6 billion years ago, all evidence suggests that our universe, the fabric of space and the fabric of time, which are kind of intermingled, actually, and all matter that's currently associated with our universe, unfolded. Okay? And so actually the universe, the fabric of space and time, has been expanding ever since. So here's where the raisin bread comes into to play. All right. So expanding universe. Each one of these dots can represent a galaxy, okay, or a group of galaxies. So here we have the local raisin. That could be us, okay. And then the breading stuff here, okay, is the fabric of space and time. So as you bake your raisin cake, okay, your breading stuff expands, okay, and it relocates your galaxies or your galaxy clusters. So here's literally what we observe. We are here, right, and we see this is another galaxy or set of galaxies, another galaxy, another galaxy. So Hubble actually, he used redshift, but could see that, for instance, the nearby raisin, okay, this is the nearby raisin, this is the farthest raisin, okay, the nearby raisin actually is leaving us at a certain velocity, okay, 2 centimeters per hour as that cake bakes, and the most distant galaxy, or most distant raisin, is moving moving faster. It's what we call recessional velocity. This is recessional velocity. Recessional speed is faster. So the farther away the raisin, the faster it is moving from us. So that's kind of where that comes from. So the point here, when it comes to motion, is that actually our entire galaxy is moving in that manner. So to kind of summarize ways that we are moving, the Earth spins on its axis. It depends upon if you're at the equator or at the poles, you know, that sort of motion. But the Earth is definitely orbiting the Sun. It gives you a certain speed. We are moving amongst our fellow stars. Okay, that's a certain random motion. We are orbiting the black hole in the center of our galaxy. Okay, our Milky Way galaxy is moving, okay, within our local group, and the universe is expanding. So we are never sitting still.